Okay, this is part 187, line 18a4e Helium 3 alpha particle decay Tritium U238 PU239 nuclear fusion engine Wow Seti. Actually, that should be 5G Wow Seti. I think because this is part of the engine deal, right? So let's just put 5G when there's a formula. Sorry. So there's your alien radio signal, and here's the alpha particle that we just looked at in the last video. So we're going to break this down and see what it's for. So this is alpha decay. In alpha decay, a positively charged particle identical to the nucleus of helium-4 is emitted spontaneously. This particle, also known as an alpha particle, consists of 2 protons and 2 neutrons. It was discovered and named by Sir Ernest Rutherford in 1899. And that's from the atomicarchives.com. So the next key word is uranium or plutonium, which is U238, and beryl plutonium, which is my idea there. I put in the word beryl there. So Google. We're going to Google nuclear reactors can be used to make tritium 3H. Because I want to know if the two of them can go together or not. Okay. So this is what I found was this thing. High energy neutrons can also produce tritium from lithium-7 in an endothermic. It is rapidly converted back to tritium in nuclear reactors 3,2He plus N plus 1 plus 3. That can be used in any reactor without exceeding the maximum allowed tritium. So the next thing I brought up was light nuclides such as tritium 3H can be used as fuel for nuclear fusion. And the next thing was helium-3. The total amount of energy produced in the 1H plus 3,2He reaction is 18.4 MeV. Beryllium is another key word that comes up with uranium, alpha particle decays, and tritanium. Helium-3 quotes from blog research. Okay, so I looked up helium-3 because I want to know what is this helium-3 stuff. Okay, because this is the first time I've heard about it actually in these videos. So helium-3 is made up of 2 protons and 1 neutron, and the isotope is rarely found in nature, although it is produced as a decay product of tritium, a component of nuclear weapons. Now, so far they haven't found it on Earth, but if it's on the moon, it's probably here on Earth. They just haven't found where it is. I think it is on Earth. I really do. But I think it's like lower down in the oceans, like thousands of feet down where we don't do any mining. It would be, because based on the age of the moon, I would go look into the rocks here that would correspond with the same age of the moon and see whether or not I'm right. The only other material that performs this proportional detection almost as well as boron, either on its own, boron -10, or in boron trifluoride, BF3. Another option is a scintillating material such as lithium -6, which emits light when neutrons create charged particles. The international collaboration of neutron scattering facilities, including J-Park in Japan, are now investigating the available technologies. Michael McGeevy of the Neutron Scientists Directorate at Oak Ridge Laboratory in the U.S., home to the Spallation Neutron Source SNS. ICIS Pulse Neutron Source at Rutherford Appleton Laboratory in the UK happened to buy 7,500 liters of the gas for its new LET spectrometer in 2008, just before the shortage hit. J-Park was less lucky, and now sits with its detectors only partially filled. Meanwhile, the European spallation source, soon to be constructed in Lund, Sweden, is banking on an alternative technology becoming available for its planned opening in 2019. Mixing helium -3 and helium -4 in a dilution refrigeration is almost the only option for reaching temperatures of a few millikelvin. Samples can be cooled electronically or magnetically instead, but these methods have only a fraction of the cooling power, so extract heat much more slowly. And I got another little graph here. So this is a model of a quantum turbulence in helium-3. Basic research into the gas is under threat too. ULT Group, Lancaster University. So the alternatives. There are 3 main alternatives to helium-3 in neutron detectors: boron -10 and BF3, which detect absorbed neutrons electronically via the resultant charge emission, and lithium -6, which detects absorbed neutrons via scintillated light. Each has its pros and cons, which is why scientists are keen to develop them all. The problem facing R&D teams is whether Lithium-6 can also be used in spectrometers, which provide information about dynamic processes at the atomic level and which require much greater detection efficiency. Semiconductor device based on boron triazolene, which although unsuitable for larger portal monitors may yet find as a use as a portable detector, and that's from John Cartwright. And these quotes were all from the www.rsc.org Chemistry World site. Okay, so we'll go on to our next video then.